Hi everyone, are you able to hear me? Hi everyone, good morning. Are you able to hear me? Hi everyone, are you able to hear?
Yes, Anirban, we are able to hear you.
Okay. Okay, so let's get started. Just 1 second. Okay, okay, good morning everyone. So today's topic is artificial intelligence, the evolution. Okay, so I am Anirban Mukherjee. So I work for Queenbay. Blibli.com basically is an e-commerce site in Indonesia. So I have over 25 years of experience in the software industry, and I lead the data science and AI team in Queenbay or Blibli. And I've been working in this role for the last 3 years and have been through the evolution of data science and AI in our field, which is e-commerce. Okay. So here you see that the Nobel Prize in physics and in chemistry in the year 2024, which is last year, was actually both of them were related to developments in AI. Now you know that when this Nobel Prize gets awarded, it's for something which is fundamentally important. It's not for commercial things and all. So this shows the fact that two Nobel Prizes in physics and chemistry were awarded for AI related things shows that AI has become something pretty fundamental now. Now, for the physics part, it's John Hopfield and Jeffrey Hinton. So these people, like Jeffrey Hinton, is called the godfather of AI. Okay, so whatever you see today in AI has a lot of it has been initiated by him, and he's still active. He's 80 plus, I think, or close to 80. And John Hopfield also made some fundamental progresses in the area of neural networks. Now, it might come as a bit of a surprise that they got physics Nobel Prize. Now, you might ask, what does AI have to do with physics? Well, it does. I mean, some of you might have worked with large language models and have seen temperature being used, okay, as one of the parameters that you have to set. So a lot of these comes from the field of statistical mechanics, which is about energy distributions of fundamental particles. So the fact that a neural network will converge and actually produce something useful had to be accepted in terms of physics before they made it into computation. And then On the chemistry side, it was not for fundamental progress in AI itself, but using AI to model protein structures. So that was one of the contributions by Dennis Hassabis, who actually now heads Google Brain or DeepMind, one of those. So he has been recruited. So he is also part of the AI mainstream community. So the point is that AI has become something very fundamental, and it's accepted that way. Okay. Uh, Now, what is this course about, and why this topic? This is actually a 2 hour session. So what we try to do is cover things at a high level to get the big picture. So lots of concepts come about. Okay. And there are lots of buzzwords that you hear, lots of things that you will hear in the media or people talking about it. Everybody seems to be talking about AI, but what does it actually mean for you, and how do you get some kind of an idea as to what this is? So that is the whole intent of this overview course, and then there are specific areas into which we can have other courses, and in your coursework also you might be having detailed coverage of certain particular areas. But this is more of getting the more about getting the overall big picture, and the target audience is anyone with an interest and curiosity in the unfolding evolution of AI. Now, this curiosity part is very important because there is a lot of stuff, and not all of it may be relevant at any point of time, but it's good to appreciate that this is a long journey that has started many decades ago. And what you are seeing today, the rapid evolution and all, has come after a lot of work and some fundamental progress over time. So if that you appreciate that, then what happens is you can map terminology and concepts into the right areas, okay, to build the concept map, so that it's not that you need to know every particular area to do work in a particular field, or work in a project, or to write a paper. So if you are able to zoom into the right area and study that in more depth, that's pretty useful. And it can get very confusing when you hear what are AI agents, what is LLM, what is statistical machine learning, what is a large language model, why is it called large, what are transformers, why are they so important? So all kinds of things you will hear. And then there will be things about, okay, GPU cost is so much, then somebody trained a model for so less. So lots of different kinds of things you will hear. Now, being able to take a look at the overall field quickly, and then be able to somehow map them both in terms of what the area is and around what time frame this thing comes from. Is it a concept which is 50 years old? Is it something which is like 1 month old? Is it 1 year old news, or is it something futuristic? So the concept map part is quite important in my opinion, and in my experience, I see that that is where people have some difficulty. That there are so many things now. What makes meaning for me? And then for those of you who are wanting to actually get hands dirty and start coding and doing development with it. So there, you basically have to know some of the areas and what the code might look like. So those kind of things you have to get into and then start using them. So you might have to know about Hugging Face and Python and the LLM APIs and how to start using that. And the most important thing, whether you are doing it for as a student, for development, for research, for industry, or for a leader trying to build AI strategy, the exploration part is very important. So somewhere it's very important to understand where all this is going, how much of it is hype, how much of it is real, how much um, can be of use to you. uh, Now, these answers are not, something very direct. It's like once you have the perspective, everybody has to make their own judgment and the decision making, basically. Now, the decision making could be for building a particular solution, or it could be about your whole AI strategy. Like it could be about, okay, how do I build this particular application where some image is scanned versus how should I bring AI into my education system. So the scope could be broad, and there are various factors that have to be sort of appreciated at least, so that you can go deeper into it for making decisions and to implement things. Okay, now, so at the end of every section, we'll briefly pause and try to recap by doing a couple of questions, or if you have any questions, we'll try to address those quickly. But yeah, time will be a challenge, so we'll have to get through the material quickly. But we'll also, I also try to see that some kind of review or absorption is there as well. So here you see the first section is introduction to AI. What I have been talking about mainly, AI is pervasive, and what are the origins, and what is the most common stuff you hear about the capabilities of machines. And then we go to machine learning and how it is different from traditional programs. The fact that you need training and inference separately, and how is it different from writing if-else blocks where you cover all possibilities in some way. Uh, and from machine learning, we go to deep learning. Now, deep learning is where neural networks start getting used, and you pretty much uh, have to use them. And to whatever is happening today is all built on neural networks, all the happening stuff. The older statistical models are used in some places, but most of the progress that you're seeing is in with respect to neural networks and deep neural networks. So they are what is enabling computer vision and natural language processing, which is the most difficult fundamental area, and which basically seems to have been cracked. And that is why the revolution of um, Gen AI and all is taking place. So point number 4, transformers or LLM, as I was saying, NLP breakthrough. So that has resulted in a breakthrough in the NLP field, which has been these challenges have been there for decades, and finally it's feasible to do these things, and that happens due to a convergence of factors. And today, the main thing is Gen AI, so generative AI, where machines generate stuff, and then the AI agents are the most talked about thing at the current moment. Okay, so this is basically the flow. And with that, we start the first section, the introduction. So the point of this slide is to show that the use of AI is expanding into more human areas. So the left picture shows what it was in 2022. So if you looked for stuff in 2022 as to how AI is impacting our lives, you would see things like uh, smart homes, IoT kind of things, security and surveillance, navigation. So they're basically machines are producing data and machines are processing them. There is, of course, e-commerce, which is more user-based, or social media platforms. There is some of those things where humans are directly involved, but there is machine-generated data, which is sort of the dominant theme at this stage. Now, coming to 2024, when you try to look for similar things, then on the right side, on the left column of the right side, you see healthcare, entertainment, education. So these are fields like which is definitely the domain of humans. Okay, they are the fact that machines would do or any of these in any significant way is definitely something very different in terms of its scope, and it can also cause some worries, and also whether this is the right thing. You may have questions as to whether this direction is at all right, but that is what is going on right now. And when you look at the other things like e-commerce recommendations, yes, they have been used here. There's a lot of data. It's been traditionally used, and it has become better and better. So when we in our companies start using LLM based models in the right way, of course, in the cost effective way, the design and all has to be proper, then we find that the models are performing much better. So what the older models are not able to do, we are able to achieve better click-through rates, and so there is a way to make use of this. So those are relatively easy ones, I would say, in that sense. I mean, the engineering is difficult, but the fact that it can be of use, there is no way humans will produce recommendations while looking at the data. But when you look at education, for example, now is should a human teach, or is it? I mean, looking for information and all, summarizing that part is okay, but should you have some AI teacher? Is that is a good idea, or is it ethical? Is it worrisome? So those kind of things are the kind of discussions that are taking place today, and there are no answers. But it's important to be aware of these things so that you can make your case wherever you are. Okay. And in terms of what machines can do, we try to capture the evolution of this. So, the programs that we usually write, so one of the earliest programming languages was Fortran, and then there was COBOL, and then C, C++, Java, Python. So these languages came, and students were learning to write, and industry people were learning to write programs, and whole software systems were used, which essentially are based on logic and control flow. Okay, if else statements, case statements, while loops. So fundamentally, that is what it is. Of course, on top of that, what problem you solve and what you do, that makes it into operating systems, database systems, or applications, mobile applications. All these kinds of things have developed over time. But these are all well-defined instructions written as code with logic and control flow. So algorithms plus data structures equal to programs. So this is pretty much the model that you write code for all the possibilities. Now, how effectively you can do that, and how much how well you design your software systems, that defines the success and maintainability and all. So most traditional and non-commercial commercial as well as non-commercial systems are of this type even today. So, and programming, as I was saying, like Fortran, I think first versions came in the late 50s. Before that, it was mostly theoretical. It was not like a lot of people were using it. There may have been some people trying to think about what programming might be, but mainstream programming started in the world from the 1950s onwards. Now, after that came machine learning. Okay, so this involves learning in some way. So machines learn to process information and make predictions. So they are working under uncertainty. So when you have conditional logic, you have if else, and then there is maybe some default case where you say unexpected error. So that is the way for a regular program with control flow. So there is the answer, but in machine learning, uncertainty is part of life. So your model makes predictions. It tries to predict based on whatever information it has, and it's trying to generalize and make predictions on something it doesn't know for sure. It's not definite what the answer is, but it's trying to make predictions. So that is the difference between non-intelligent programs. Now the developer may be very intelligent and have done it very right, but the program itself doesn't have the capability to learn. But in case of machine learning, yes, the model can make predictions. It can, how it does is, of course, there are various different kinds of models. And then with retraining, it can get better over time. So if you give it new data or feedback on how it has performed, then the model gets better. So the learning part comes in the machine learning, and what comes here under this field are predictive analytics, logistic regression, support vector machines, decision trees. So these kind of things. So they are not if else while kind of things, but most based on data, you find some statistical pattern or other kinds of patterns, and then try to predict. So, and in the mainstream commercial stuff, um, they have been from about maybe 2005 onwards, I would say. Yeah, does anybody have any question? I can see a raised hand. Okay, I'll check the chat 1 second. Okay, so okay, yeah, so we'll carry on. Okay, now after as machine learning evolves, we get into artificial narrow intelligence, and that is where we are pretty much. Okay, so the machines start doing some human-like tasks. Okay, and then we start calling it AI. So, for example, you know, so the AI/ML is the term used for such things: object detection, summarization, translation, specific tasks. For object detection in images, then summarization of text, translation of text. So these are specific tasks, but these are relatively high skill tasks because these are the domain of humans. But each system is doing one kind of thing only. So they are specialized for certain things. So there is one model which will do object detection, and then one which will do text summarization. And from there, within narrow intelligence itself, we evolved into this chat GPT world where it's the human can converse and ask it to do various things. So it actually can do various types of tasks. It's not specialized for one task. It's specialized for carrying out general instructions, and that too by interacting with humans in human language, not programmed. Okay, so that is sort of a more powerful form of artificial narrow intelligence, but it's still not what a human being does, like being able to analyze and do a lot more of logical things, and then learn new things by itself, figure out what to do, what to learn. Those kind of things are still not there in artificial narrow intelligence, but going in that direction. So AI agents, for example, have some are an evolution of the Chat GPT kind of or the LLM kind of things, which can do some of this. So that is this the whole artificial nano intelligence. You can say from 2012 onwards, we've been having this kind of stuff. Okay, and now artificial general intelligence is AI with human level intelligence. Now, this is actual machine intelligence. People have started saying that it is 5 years away, but nobody knows for sure. Okay, and but that's sort of the idea that this is human level intelligence for AI systems. So machines understand what they are doing. Okay, they're able to perform any intellectual task that a human being can do. So some people, the most optimistic estimates put it at less than 5 years away. And then is artificial superintelligence, which is the domain of science fiction, where AI surpasses human intelligence, and then it is conscious and it has its own identity and it can think. So that is definitely nowhere close. Nobody thinks it is anywhere close. So it's at least 10 years away, but these are all very optimistic estimates, probably. Okay. And here we sort of show this graph where the exponential progress that has happened and is being predicted is shown. So whatever you see, this is basically you can say artificial narrow intelligence. AlexNet is a particular type of neural network, and AlphaGo is a game where and some kind of advanced chat you can think of. And then the transformer architecture, as we will see, has been a breakthrough in the NLP field, which has enabled today's revolution in Gen AI. And then Alpha 4, Chat GPT, GPT-4 was much more powerful than GPT. And then AI agents, all these things are happening. And the prediction is that artificial general intelligence would be reached after 5 years. And maybe artificial super intelligence, we don't know, but that's something which is whether artificial general intelligence or super intelligence will actually happen, nobody knows. But how do you know that it has happened? If the machines are doing a lot of things which humans are doing, then we have to learn to use them, the consequences, and positive and negative both, basically. Okay, so I see some raised hands. Any questions? Okay, so we go to the beginnings of AI. So actually, the term artificial intelligence was coined in 1956, so a long time ago. And this is where there was a lot of talk about what machines can do. Even before, I mean, around the time when programming languages started, at that time itself, the limits of what machines can do, whether machines can imitate humans or do what humans can do, was already coming into the picture. And Alan Turing proposed the Turing test in 1950, where you have a machine and a human or a human on the other side of a screen, and then a human tester interacts with that, what is hidden from their view. They pass questions and get the responses. Of course, the medium for that was not so advanced. It was like printed paper goes in, printed paper comes out kind of thing that was thought about. But the idea is that on the other side, if the human tester C can't make out after a long time, after a good amount of interaction, whether it's a human or a machine on the other side, then the machine has passed the Turing test. And then John von Neumann, after whom today's von Neumann architecture for machines is named, proposed self-replicating machines in 1950. So a lot of thinking about what a computer or a machine could do or look like or be capable of was being imagined a lot before actual machines were built. The machines which were coming out at that time were very rudimentary, but in terms of theory, what is happening today, the seeds of that were laid like in the 50s itself. And but the evolution of the field did not happen in that line. So after that, there was some fundamental difficulty in carrying out the ideas of artificial intelligence and all. So then commercial software systems started getting built on the mainframes and all. And then from the 90s or the late 80s, commercial software became very popular with the PC and the lower power, the less powerful personal computing machines when more developers got in. And after the decade with the internet and all, data started getting generated in for various things. So the data became extremely important, and the fields of big data and then data science, all these things came in. So first it was data engineering, like how do you collect and store data, how do you process it, clean it, and then comes data analytics. Once you have the data, how are you able to analyze it and find out various insights from it? And then it goes into data science, where you actually not only process, analyze, and find insights, but you make predictions. So the making predictions part is all where the data science comes in. And as part of data science is machine learning, deep learning, the computer vision, NLP, as the type of data changes. And all these things became possible because of a lot of progress in hardware, networking, and software. So it was a natural evolution. So commercial software produced a lot of data, and then with the cloud and all these things coming into the picture, which was accessible to a lot of people, and that was enabled through advances in hardware and networking. So then today, when you look at the AI field, it's very much data driven. So information is more fundamental than logic. The early systems were more like, okay, I can logically analyze. If given a lot of rules, I'll be able to put them together. I mean, not I, I mean, the machine would be able to put them together and be able to do things. But then it evolved into something like, okay, data is the more fundamental thing. Once you have the data, the machine is able to capture patterns from it and be able to reason about it and make predictions. So that was some kind of a shift which happened in a subtle way. And to drive home that point, we take an example of sales data. So use cases related to sales data. Now, once you have sales data in your database, now the first thing that came about was static sales reports. Okay, so these are SQL query based, direct SQL queries, and they are run maybe once a month, once a week. And you have your group by and aggregations, and you say that by this region, these this much of sales, and these are the trends over time. So those things can be done by direct SQL queries. Now, business intelligence is the next level, where this is made more usable, where you have dynamic dashboards. It's not like static reports getting generated by running SQL queries once a week, but it's like anytime somebody can go in, look into the dashboards, drill down, roll up. They can do it dynamically and see all of those whenever on demand, basically, and see many things together. So From there, it evolved into the predictive analytics, which is machine learning based. So this is where the machine learning part comes in. So for sales data, it will be not just, okay, sales were going in this region in this way, the growth was of this type, revenue grew so much. Not just that, but okay, give me find the top 10 uh, sales opportunities with the highest likelihood of success, and suggest what should be the next actions that the sales people should do to improve their chance of conversion. So that is a predictive analytics use case, and machine learning systems would do these things. And now, once you do it from structured data in the database, it is of one type. You can use certain types of statistical models. But when you have, salespeople's emails or pictures, brochures, so those kind of things have to be analyzed. Like images, text have to be analyzed, not just structured numerical data or categorical data in tables. So then you start requiring neural networks for meaningful progress. So that is when AI, ML, deep learning came into the picture for similar predictive analytics, but it was not restricted to processing information in tables, but they could take unstructured information and do the same kind of things. And finally, with LLMs, we have generative AI. So now we're not only analyzing, but generating new content. So after doing this analysis, you decide to run a sales campaign. Now, what should that sales campaign contain? We use generative AI to create those brochures, ads, stuff that usually the digital marketing people would be doing, humans would have been doing, but now they can use generative AI tools to do some of that quickly. So this is some kind of a high-level overview of the evolution in the industry of this whole field. And here we see artificial intelligence, machine learning, deep learning. What are the differences? So I think it's not so important to be caught up in the exact differences, but these are all guidelines. These are terms which have become like de facto definitions. So artificial intelligence is the big thing. Okay, so ability to learn and reason like humans. Machine learning is more restricted in scope. That is what is in wide use today. I mean, in every part of your life, you are actually knowingly or unknowingly interacting with machine learning systems. And deep learning is the subset of machine learning, which basically involves deep neural networks for processing these computer vision and NLP use cases. And if you look at transformers and all, they are deep neural network architectures only. So that is the area, and that is the area which requires a lot of computation power, GPUs and stuff. So if you are not using those, then you don't need GPUs. You can do with less processing typically. So that's sort of the context of this. These terms keep coming all the time. So it's good to see that in the introduction. So now we come to the end of section 1. Let me see if there is anything. Okay. So now let's do a couple of simple questions. Okay. Just do 2 of them. Which of the following are key? You can see, right? Everybody can see the screen. Yeah. Okay. So now, which of the following are key factors that have contributed to the evolution of AI? So yeah, advancements in computing hardware, definitely. So we saw the deep neural networks, and today computing hardware is a major concern. Okay, NVIDIA GPUs, you must be hearing about all the time. And then increased availability of data, we talked about this. Okay, decline in internet usage, that is irrelevant. And development of complex machine learning algorithms. So these have definitely contributed to the evolution of AI. And this is also trivial, like we name these people. So Alan Turing is known for the key figures in AI history and their contributions. So Alan Turing for the Turing test. John McCarthy coined the term artificial intelligence. And von Neumann talked about self-replicating machines. Okay, so Isaac Newton, that's a joke anyway. So he had nothing to do with this. And it's long before also. So the self-replicating machines, let me just mention what it is. So it's machines with intelligence which can basically, in some cases, in some sense, replicate. They can produce copies of themselves. So you can imagine a robot which can use the materials in its environment and make another robot which is also intelligent. So that is the whole vision of self-replicating machines. So okay, now we come back. um, okay, now we go into machine learning. So this is, as we saw in the Venn diagram type thing at the end of the last section. So it's a subfield of artificial intelligence. The important thing here is that your programs now get divided into two parts. There is the training part and the inference part. The inference part is what actually runs. So when you are hosting a service, or when you are actually making predictions, you are using the model to do inference. And the preparation of the model to be able to do the inference is what is called the training. So, and the training has its ML algorithm that you use for the training, and the data. The data is, of course, fundamentally important. So the data is going to be used by the machine learning algorithm to create the trained model. Now, the difference, as we saw, this is, it's not explicitly told to given rules or conditions to evaluate. It's just given the data, and then it's able to pick up the logic in some sense, or the patterns in that data, so that when you give it new data, it is able to make predictions. So that is the inference. So an ML algorithm can adjust its own settings given feedback on its previous performance. So this is the learning part of it. So suppose the model is making predictions as part of the inference. Now, somewhere you have to know whether those predictions are right or wrong. Okay. And this is often a very challenging area in machine learning. In many cases, you have to do some kind of an audit by humans again to see whether the predictions were right. That is not ideal, but that is sort of the only choice you have in many situations. And then the feedback about those errors. So those errors could be false positives or false negatives. Say, for example, your model has to see an image and predict whether it's a prohibited drug or not. Now, a false positive would be the case where you say it is a prohibited drug. Your model says it's a prohibited drug, but it's not one. It's not a prohibited drug in reality, but your model says it's a prohibited drug. Now, what is the impact of that? So, as a result of this, you will block the sale of it or put it for human review. So, needlessly, some work is being generated for human reviewers, or the sale which could have happened has been blocked for some time until review is completed. So, this is the negative impact of false positives in this particular use case. Now, false negative is where you did not detect. You said it is not a prohibited drug, but in reality, it was. Okay. So that is also a problem. Now, in your site, prohibited drugs will appear for sale, and for reputation, or for so Google or Apple will also run programs on your mobile apps to see to try and detect if your app is doing such things which are illegal or not allowed by their policy, and they may flag those. Okay, so that is, and then your reputation, and they may remove the app from the app store. So that is the kind of impact that false negatives can have. And the model will never be perfect, but if you can reduce the false positives and false negatives to acceptable values, like and what happens is, in reality, they can be really, really good. I mean, they can come down to 99.99% and all. So, for example, in Blibli, we have about, like, on some days we have 300,000 products being uploaded by sellers, and they all have to be checked for these things. Now, who will do that? Okay, it's impossible for human beings to see 300,000 items in a day. So these ML models, they flag these products and block them. In cases where they are certain, it's completely blocked. And in cases where there is a bit of uncertainty, they put for manual review. And maybe 1,000 of them will go for manual review, and those 1,000 will be looked at by human reviewers, and then they may say, okay, these are actually fine, or no, this was a this was an actual block that should happen, and they'll block it. So that's how this kind of automation helps. It reduces the work, and as long as the model has low false positive and false negative rates, it's good for everyone. Now, coming to the training and inference part to understand this. So now a traditional program, you have written code in the program. It takes the inputs and produces the results. So this is something everybody is familiar with. Now, in case of machine learning, it gets divided into two parts. Finally, what runs, just like the traditional program, is the inference part. So you have the model hosted as a service, or you might be running a job which uses the model. So take the inputs and produce results. So in this sense, it is similar to a traditional program, but there is no program actually. There is no code which says these are the rules. There's the model which is there. So the inputs are passed to the model, and that might involve some pre-processing and all, but that is all data stuff. But the model actually is producing the results or predictions. Now, how did the model develop the capability to do that? That happens to the training phase. So there are inputs provided to the model along with, usually there is it's called supervised learning, where the result is actually also correctly known, and you use that training set to give it the inputs and the results that are expected, the correct results. And the model learns how to make predictions on new data. So the model updates its own internal weights or parameters so that it can model the distribution that of the input, so that when it is presenting with new data, it basically makes a prediction. So I said, I talked about distribution. So most models are actually statistical deep down. Okay. So even neural networks, even the vision models, somewhere it is finally it's a very complex probability distribution. And by the generative AI is actually the sampling of that distribution, and the predictive is basically you are sort of making predictions based on the distribution, so discriminative. So but to build such a huge joint probability distribution with so many parameters, it requires neural networks and all. Though it might appear hidden, that it might not be directly talked about as a probability distribution, but that is what it fundamentally is deep down, any kind of model. And there are models like, let's go to the next example. We cover a name-based classifier. So those are directly known statistical models with a limited size. So here, the summary is that an ML algorithm can adjust its own settings given feedback on its previous performance in making predictions about a collection of data. Now, this previous performance, as I was talking, so wherever the model made mistakes, if you give that feedback and retrain the model, then it should improve basically and do better next time. So that is the learning for simpler models. Now there are models which can learn even without being retrained, and those they are given rewards or some kind of feedback, and that is called reinforcement learning. So there is a variation on this, but right now let's stick to this. We'll cover a bit about reinforcement learning. So, okay. So now let's take this use case of spam detection, where we are passed in an email and we have to say whether it's a spam or not. And here you see what this program might look like. So on the bottom are many patterns which capture basically words or patterns which appear in spam emails. And this is handcrafted. By looking at spam emails, somebody lists this down and maintains this, and then the code basically opens this spam words.txt. It knows all, it reads all these patterns and gets ready for its processing. Now you could have all these things inside the code also, but that would be quite unmaintainable. So that's why we put the patterns in a separate file called spamwords.txt, which has the words and patterns. And then you take the email body and then call the isPam function, which is on the left in bold. So what would this spam function look like? You would first check that do any of the words in spam words match. You could use a regular expression for the whole thing as I have shown in this file, or you could check one by one, whatever. That's not important. There are various, you have to do it in the most effective way programmatically. And then check for all caps words. There are various kinds of rules that you are explicitly checking. And if you want to introduce a new rule, you will have to change the code. You might have to change the order of the checks sometimes, so that You are not checking for something after you have already checked a broader condition on top. So it becomes a lot of work to code and maintain. But yeah, a lot of times that's the only choice you have, and that's how it is done in traditional programs. Now, how is it different in machine learning? So in machine learning, you don't start with the program at all. So what you do is you have the data. So you need some labeled data. So there are mails which somebody has gone through and classified into spam or not spam, which is ham. And the content of that mail is in the text column. So you have the text and the labels. Now, using this data as starting point, you do training. So here, a multinomial knife-based classifier is being trained on this data. And for doing that, this is text. Now, how will the model use the text? You have to convert it into something numeric. And there are ways of doing it. So in this case, it's using a TF-IDF vectorizer as pre-processing of the data. And then it's basically generating TF-IDF vectors for each spam email, and then doing training a classifier basically using the label and the vector for each mail that it has generated from the mail. So after this classifier model has been prepared, now you have the inference separately. The inference basically uses this model. It loads the model. I haven't shown that part where to save the model and to load the model in this inference. So the model is available to the inference code, the model which was trained in the training code. So now you take the model and then you use the predict method of the classifier to pass in a new email, and then there is a prediction which is given by this predict spam. So the part in italics on the left side below is the main function, and the predict spam is the function. So now you have two programs, one for training, one for inference. Okay, and you started with the data. So that is the fundamental thing to capture. Now, for processing images and text, when you have to process images and text in large numbers, then your if else and all becomes quite difficult, and even the statistical models with numeric things also become very difficult to use. There is a lot more processing involved, and this is where neural networks are essential. So for both processing of images and for processing of text in a more detailed way, in a more elaborate way, where you have summarization, question answering. So for text search or information retrieval, you might be able to use the TF-IDF, which is also called a bag of words model. So it doesn't have the context and many kinds of the human language stuff is not there. It's an enhancement on the keyword match to take care of frequencies and importance of certain words, but it's like a group of words, not with much context or order in it. So that kind of thing can be done by other models, but for proper computer vision and natural language processing, you require neural networks and also deep neural networks. Deep means it has many layers. So we'll see a bit of that after this. So for processing images and text, the neural networks come into the picture. And so this is the last slide in the topic of machine learning. So these terms you will come across often: supervised learning, unsupervised learning, and reinforcement learning. So supervised learning is what we talked about in the example. So you have the data and the labels. So whether it's a spam or a ham. So that kind of thing, somebody has to generate that data. Now there are often cases where such data can be generated much more easily. Okay, and a lot of the LLMs and all do that, called masked language modeling or next word prediction. When you already have the text, you might be able to cover some parts of it and use that as a supervised learning. But in general, you need somebody to create label data. So collection of data and producing good data sets becomes important. In unsupervised learning, you don't have labels. You just have the data, and the goal is to learn underlying structures. So there may be clustering based on features. So for distinguishing between apple and orange, there would be all kinds of parameters that you collect for the fruits. Okay, the weight, the volume, then the length, breadth, diameter, color. They could be numeric or categorical also, like color and all also can be used. And then it will try to your algorithm will try to cluster. So those are unsupervised learning, and reinforcement learning is it sort of learns on its own. It doesn't have to be retrained, but based on the performance, it's there itself the reward is provided online, not as a new retraining. But if it made a mistake, then there is to know that it made a mistake, and then it will basically sort of update itself. So reinforcement learning is essential for logical reasoning and stuff, which are where LLMs have now reached. Okay, and applications of machine learning, NLP, computer vision, search recommendation systems, medicine, biology, image generation, playing games, robotics, other applications. So these are very standard now. It's widely used in all kinds of systems. And if you anybody who has to work on software development will come across this along with your regular logic based programs. Some elements of this will always be there. So okay, now we do a couple of questions here on this topic. Again, these are very simple ones, and anybody who is awake will be able to answer these correctly. Okay, so there should be boxes here. By mistake, the radio buttons are there. So first one is correct. Okay, ML algorithms are just based on data feedback that we discussed. ML models require explicit programming for every scenario. So this is not right. This is incorrect. Okay. ML models can be made to improve over time. Yes. So in case of regular supervised learning, you have to do retraining. And in case of reinforcement learning, there is some kind of way of providing feedback directly. The feedback is also defined by the model, and it's collected from its operating environment, as it is called, and then it improves itself. There is no explicit new training that is done. It's continuously trains itself. And then traditional programs cannot process large data sets. No, that is also not right. Okay. So the correct ones are this one, the first one, and the third one. Okay. And now question 4, which of the following are essential steps in training an ML model for supervised learning? So let's restrict to supervised learning, which is the most common one. So is data collection and pre-processing. That is always required, whether it is supervised or unsupervised. And then model training using labeled data, yes. So manually coding all possible programs, no. That is not what models are for. That is what traditional programs are for. And evaluating model performance. This you have to evaluate. It's not enough to train. You have to get feedback about its performance and then basically improve it if required, either through retraining, or if it's a more elaborate reinforcement learning, then it should be able to do that on its own. But still, you have to audit and check whether it's doing that right. Okay, so now we come back. Okay, and where do we come back? We come back to deep learning. Okay, and deep learning is basically all the neural networks and GPUs. So this is deep learning. This is where it starts. And then you have things, transformers and LLM are development of a particular architecture called transformers on top of the deep learning neural networks. So see, the difference between machine learning and deep learning using neural networks is about features. So in the top figure, okay, if you look at the top half of the top figure, machine learning, and below you have deep learning, and then you have a figure below also. We'll come to that later, but let's look at the upper figure first, the upper left one. So in machine learning, from the input, features are extracted. Now, what is feature extraction? Feature extraction is basically the data scientist analyzes the data, and then the use case, basically what needs to be predicted, and then we will study and they craft features and check the distributions and see that what kinds of things may help here. So, for example, if a car has to be predicted, now here is an image of a car, but let's take a simple case of where you have, other data about the car available, and you want to predict the type of car. Not exactly what is shown here. Here it is an image-based thing, but they say you know the engine power, you know the how many how many drive, basically, whether it's a two-wheel drive, four-wheel drive, then how many seats it has, how many windows it has, whether it has fog lights, whether it has um, you know um, rear window defogger. So there could be numeric things like your engine horsepower, and there could be Boolean things like does it have this or not this, or it could be color, is it red, blue, green, whatever it is. So these are potential features, and the data scientist may decide to combine some of them to produce features that are more indicative. There may be a lot of redundancy in features. Say, for example, a red car is always a Zen. Suppose in the data set that is the characteristic, so it's no use having color as an attribute. So feature extraction is about studying all these and then handcrafting features that are going to be useful for the classification. But that's not what you do with neural networks. With neural networks, you don't handcraft features. So the neural network is provided the whole input and the output label, and then it undergoes some very computationally expensive training, and it's able to somehow within its network of weights and parameters, it's able to encode all this information by itself. And it basically the latent features, latent is something which you don't see directly, so but it is present. So these latent features are automatically computed, and those features may not be the same as the kind of features that humans are seeing. Okay, so somewhere inside the network that is being coded. But for an example, on the lower figure, we have uh, features which for an image processing use case also, you can have handcrafted features like you might try to calculate the roundness of the face, the distance between the eyes. So these are limited image processing that you do on this to extract features, then the nose width, eye socket depth, cheekbone structure. So these are explicit features that the classic machine learning program, the AI programmer may, or the ML programmer may try to derive these from every image and use these to train a classifier algorithm, which could be a support vector machine, random forest, any of these things. And then the label is Mark. Mark is the name of this person. So this is Mark's face, basically. So now here, the features were manually extracted by processing the image, and not manually extracted, I mean, basically handcrafted. So by running programs only, but you calculate all these things by processing the image using other techniques, not neural networks. So it may be easier to do these things. Say, for example, if you have handwritten text, you may take the grayscale image, and all the blacks would be weight 1 and all the whites would be weight 0, or the other way around, and then you calculate the center, centroid, then the moment about the center, then the length of the boundary. You would be able to calculate all these by just doing two-dimensional array processing, and then you could use those as the features for a classifier algorithm. But with a neural network, you will pass the pixels directly. Okay, so those are your inputs. And then there would be, in this kind of case of an image, there would be a convolutional neural network with layers, and the label would be provided, Mark. And then if you have lots and lots of these images, if you have enough data, the neural network will get trained, and it will basically discover its own features and set its parameters internally. There won't be any handcrafting of features. Okay, and now we look a bit more into what a neural network looks like. So on the left, you have a 1980s era neural network, which is a neural network with a shallow neural network. So the input and output layer will always be there in a neural network, but the number of hidden layers may vary. So if a network has many, many hidden layers, now on the right side, we show only 3 hidden layers, but usually it will be like tens or hundreds of them in today's neural networks. So, uh, so the input and output are always there, but if there is only one hidden layer or less hidden layer, they're called shallow neural networks. And if there are many hidden layers, then they are called deep neural networks. And as I said, deep neural networks will have like typically 50, 100, or several hundred today. Okay. So, and that the layers and their connection and what type of units they are, that defines the neural network architecture. So here, if you see on the deep learning neural network picture, so there is a picture which is of a person which is parked. That's actually George Washington. And then the network is actually able to say that it is George out of the four possibilities. Okay, so there are four people whose images it can predict, and it correctly outputs a given image that it is George. How is it doing this? It's not doing any feature computation, but people have studied what each hidden layer is doing. Okay, what is the output of each hidden layer to try and explain how it works? And what they have found is, say, after the first layer, the edges are identified. Okay, so you have edges being identified there, basically edges in the figure. And then the second layer, actually, whatever it is outputting, it's not instructed to do so. Nobody has programmed this network to identify edges, but it has figured it out on its own somehow. And then the combinations of edges to form certain shapes is done by the second layer. And then the third layer is actually taking those combinations of edges and identifying facial features like eyes, nose. And then finally, the person is identified. So this is what happens internally. So these features, nobody is telling the network, but the network is only being given data, images and the label, and it is being trained through an algorithm which we will see next, back propagation algorithm. And then finally what we show here is the forward propagation of the inference. It's given an image and it predicts after it has been trained. And while it is doing, it's actually latent features like edges, combinations of edges, it is discovering by itself. Okay, and that we don't know how it does it. So that when something, so that is why these people like Hopfield and Hinton got Nobel Prize, because they came up with something where it's able to do these kind of things. Basically, somewhere there is some kind of brain type function. Whether it's the same or not, we don't know, but something fundamental is there. And although neural networks were thought about in the 50s and all, from that time, so we see them being applied today in a big way. And that has been due to the evolution of other things like big data, hardware, software. It's become possible to do such heavy computation, and there is enough data to do that. So if you think of somebody in the 60s, they would have had access to none of these. The idea might have been there, but it was very hard to put this into practice. So they tried and failed, and there were AI winters that came, and for many decades people kept trying. And as when things finally caught up, and when the community could also get involved, so that's also something important which happens in technology, that when large numbers of people are able to contribute, then progress happens. So big data, hardware, software have evolved and led to this convergence, which makes neural networks practical today. And here I just show these, we won't get into this, but the perceptron is the building block of the neural network. So these are covered in any neural network course. These are important theoretical concepts. And we show the single neural network. And so every layer computes its outputs, which are passed to the next layer. And then finally, there is the final output. So these can all be modeled as vector operations, matrix multiplication, and vector calculus, basically, where you minimize the loss of a function with many variables. So that is the loss optimization thing, and how you optimize the loss of such a thing is usually by gradient descent. So the choice of loss function is important. It's something which should have one minimum, and then the gradient descent will converge. So when you are using neural networks, it will be activation function, the loss function, and some of the gradient descent parameters are things that you will usually have to set if you are working on this, in addition to putting the right input and output layers onto some available network architecture, because the input and output define what it does finally. I mean, although, yeah, the other thing about that I wanted to say is if you think about the previous slide, so you could take the first two layers of the first two hidden layers, which is able to identify combinations of edges, and then not use it to identify facial features. You move off these things, and then you may use it to identify faces of dogs. Okay, so that is the power of transfer learning. So you may be able to, and so for even for detecting the face of a dog, the edges, combinations of edges would have to be identified. So that is why it is possible to take an existing neural network and then fine tune it with new data, put in new layers towards the output, and retrain with a small amount of data, or that's called fine tuning. And then it will be able to do a new function. Now your output layer would change. It would be the names of the dogs in that case, not the names of the people. So that's how transfer learning is important. And that's how why you hear of so many models being built, because people take the work of others and then they're able to easily adjust and extend it to other use cases. So the neural network training happens through forward propagation, through the back propagation mechanism. So when the neural network starts from when it is fresh, the weights are all randomly initialized, but then inputs are passed through it and the output is computed. Now that output may be wrong, in which case the loss, which measures the difference between the predicted value and the actual value, because it's labeled data, you know the actual value. That loss is calculated, and then the network weights are updated through the backpropagation algorithm to minimize the error, so that when the next time the image is passed, the loss will be less. Okay, so it will be able to make a prediction. So this has to be done like many times. So each pass through the data set, one pass through the data set is known as an epoch. So after one epoch, it will have some performance. It will still have high losses, and then you go through multiple epochs of training. So the thing is, there is a lot of data that is required, a lot of computation that is required, and data is not like any data. You need label data, or you need data from which you can generate label data easily, which is the case in a lot of the NLP use cases and LLMs. Okay, so the backpropagation mechanism basically is vector calculus based, and it uses matrix multiplications. So you can do these in parallel for billions of parameters. So we are showing these nodes and these connections, right? So each connection is a weight. So when you hear of a 175 billion parameter, roughly it means that there are that many edges with weights in them. So 175 billion of them um, are involved in the computation. So in the forward pass, when you are doing the inference, basically there is only one this forward pass to the network and the prediction comes out. So that is less computation and also less memory intensive, because you don't have to store state. Now when the back propagation has to be done during the training, so you have to go, then you calculate the loss and then come back and update the weights layer by layer to minimize the loss. And that requires storing some state while during the forward propagation. So one of the parameters that you might see in a neural network is whether to store gradients or not. So for inference you disable that, but for training you have to keep that, because these gradients are what or these gradients are basically combinations of partial derivatives with respect to all these parameters. So vector calculus basically, which allows you to now update the weights in a way that will minimize the loss. So it's a function minimization problem, but the function has billions of parameters. Okay. So now we come to NLP. This is the thing which takes us to the next topic, which is transformers and NLM. So NLP has always had major challenges. It's hard. So it might appear that images have a lot of things, but actually images have much more structure, and you can break down images into smaller blocks and analyze those blocks and with convolutional neural networks. So those things are much easy, actually simpler. I mean, that's also hard, but language is much harder, okay, because it involves human expression. Now here I have put a food for thought. So if you think of human history, language has come about only in the last few thousand years at most. Okay, and maybe proper languages are even less old. But uh, communicating through expressions or identifying objects or identifying things, identifying whatever is needed to survive has been going on forever. Like, and animals also are able to do it, and birds. So those are sort of image processing things fundamentally are uh, sort of more basic than language. Now, and in natural language processing, there is the natural language understanding. So you have to understand the instruction, and then the generation, which is all this generative AI. Generative AI does it not only for languages, it does it for images and all, but the whole communication medium is language. Like you instruct the Gen AI platform or the LLM model using instructions in English. You ask it what to do, so it has to understand what to do, and then it has to carry out those actions. So that is and produce other text or stuff. So that is generation. So NLP, we are not going to go into this, but what I want to emphasize is that it also has a long history. This field had a long history along with the rest of machine learning. So NLP was one of the sticky problems and the one which never worked all that well to the satisfaction of people. And so there's a whole field. So deep learning, after deep learning came, so even before deep learning, actually, I want to cover this the shallow neural networks for embedding. So that is very important. So that is one kind of breakthrough. And then sequence models using deep networks, but the networks that we showed for images don't work here. So you have to use recurrent neural networks or long short-term memory networks, and then there are encoder-decoder architectures. So the main thing is NLP requires a different approach. And one of the challenges of language processing is context. The same word may mean different things in different contexts. Then you may have to associate the subject with the action or the object with the action. So for any long sentence, you yourself, when you read a long sentence, there is a lot of context in it and association of things. So it's a high level skill basically that is involved. And here we look at embeddings. So on the right side is embeddings. Embeddings is something very fundamental. So if you are going to be working in AI today, use of embeddings is like all over the place, even for simple models. So anything to do with language processing will involve embeddings. And those embeddings could be at the word level, sentence level, document level. So you might be able to achieve some good results quickly for some simpler tasks just by using the right kind of embedding. And you may even use those embeddings in a vector database for retrieval, and even without having LLMs or any majorly trained model, you might be able to produce applications quickly. So here on the left, we see what are called these bag of words kind of model, where which is easier to understand. So you your text is broken up into words, and all the words in the text, after some filtering, you don't want the most common words and all. So you form the vocabulary. So the vocabulary is computed. So this is a regular programming. So you separate by space or white space and then collect all these words and then form the vocabulary. Now, for any particular sentence or document or whatever is your unit for which you are producing this vector, you see, you basically for each word in the vocabulary, you mark its frequency. Okay, how many times does it occur? Okay, and that's called a bag of words model. So this is a word frequency model. You might extend it to have TF, IDF kind of model, which is a bit more processing, but fundamentally the same kind of thing. It's a bag of words model. The order of the words, it doesn't matter. It's more the frequency. And in case of TF, IDF, how rare it is, how important it is kind of thing. But finally, you have this kind of a vector where every item of the vocabulary is present, and most of them will be empty because one sentence, if you're doing for a sentence, won't have all the words in the vocab in the whole collection of documents. So then you need some way of compressing those or doing the sparse representations. But embeddings are dense. Okay, now embeddings in Spirit are similar to, again, finding latent features as we saw in case of neural networks. And usually neural networks, shallow ones are good enough for producing embeddings, simple embeddings. Now, the embeddings used in transformers have context also encoded into them. They require much more heavy processing. But here we are talking of, say, word to vec kind of embeddings, where what is happening is, see, you have, if you look at every column, that is a word. but the attributes are sort of latent features. And for simplicity, I mean, for our understanding, it is shown as animal, newborn, human, plural, fruit. Okay, so all, these are latent features which it has itself discovered. These features were not provided. These were automatically computed, and it is not animal is not what it determined. It found something which, when we look at, could mean something like an animal. And there are scores for each attribute. So now you have a dense vector with attributes which the network itself figured out from the text that was given to it, from the data that was given to it. And then these embeddings I mean, they can be done at different levels. You could have word embeddings. Now, in this particular kind of word to vec, let's say, each word will have a unique embedding. So if the word is used in two different ways, it won't have two embeddings. But when you get into contextualized embeddings, which is what is produced by the encoder part of bigger models, so there you those the encodings it produces will depend on the context. Like for that segment of text, it will be one thing, and for another segment of text, it will be another thing based on the meaning. Okay, and then so the lot of this NLP progress is about handling these embeddings in the best way and being able to handle large sentences and large context. So it's a difficult and non-trivial field. It involves a lot of things, but it's important to sort of appreciate what embeddings are, and because it's very widely used. Okay, now we come to the end of this section. So we'll again go to the couple of questions for this section. What are the key differences between machine learning and deep learning? So yes, deep learning relies on neural networks. Deep learning requires less data than traditional ML. That is definitely not true. Machine learning models typically use feature engineering. So yes, if they are not neural network based or deep learning, then they use the. I mean, here machine learning means the other machine learning. Of course, deep learning is a subset, but if we what is meant here is the other stuff, not the neural network based ones. And deep learning automatically extracts relevant features. That's also true, as we discussed. Okay, what are the common applications of deep learning in NLP? So sentiment analysis has been a popular case. It has been done with non-neural network approaches also, but this is what has made it work. Object detection in images is not an NLP problem, it's a computer vision problem. Machine translation, text summarization, so these are all machine learning, deep learning or NLP use cases. Okay, now let's go on to the next section. So transformers and LLM. So for the last few years, this is where all the buzzwords have been. Okay, so the attention is all you need paper was a breakthrough which introduced the transformer architecture, 2017 paper from Google by Ashish Vaswani and others. So, and then this basically said attention as a concept was already there, but this said you can use attention as a much more fundamental building block of these networks or these systems. And along with that, another development is Hugging Face. So any of you working in AIML will very soon already know or will soon know about Hugging Face. This is sort of a central repository for models, particularly transformer based models. So they will have versions for different frameworks. Like today, of course, PyTorch is the more commonly used one, but there could be some which have TensorFlow based implementations also. So Hugging Face is something which developed during this time as a model hub. And so anybody puts their model up there, any open source model basically, so that others can use. And so attention led to powerful context handling capability in LLMs. So BERT, GPT, these are the models which came from Google and OpenAI respectively. And the large transformer model. So the transformer is a neural network architecture, okay, which is described in that paper. So it encodes context and it has encoder decoder. So there are details, and it has a certain way of representing this. And once, so it was able to produce very good results in handling context, which has been the challenge of NLP for many decades. So the giant transformer models, they started being called LLMs, or large language models. So they have tens to hundreds of billions of parameters. The parameters, as we know, are the weights of the neural network, the number of weights of the neural networks. You can imagine how big they are. So GPT-3, GPT-4, and Chat GPT is the web interface that people use. The backing model is GPT-4. That is the base model. So we'll talk a little bit about base models, foundation models or base models, and the fine-tuned models. So the model that is used by ChatGPT is an instruction-tuned version of the GPT-4 or GPT-4o, whatever it is now. So they started showing generalized capability and emergent ability. So we'll talk about that also next. But in terms of the timeline, again, a lot of development since 2017, very fast, lots of milestones. But before that, if you see from 1997 to 2007, it was stuck at LSTMs. So NLP had hit some limits. So after the RNNs, and then came LSTMs, and after that there wasn't. It was sort of stuck at one place. But the transformers led to this whole new set of things coming in that we see all around us now. Okay, now the emergent abilities of LLMs are what is making it a rage today. So when the model size became big, when they were based on the transformer architecture and they crossed some threshold of number of parameters, then these models started exhibiting qualities that smaller models were not able to show, like in context learning. Now, so the prompt is an instruction that you give to an LLM in human language. Now, as part of the prompt, you could include examples in the prompt itself. So there is one thing called fine tuning, which we talked about, where you give it new data and you then train it for a different task. So it can understand English, but can it now be fine tuned to sort of determine sentiment? Okay, so that is fine tuning. But here, in context learning is okay, it understands English, but now you say, okay, here are 5 examples of positive and negative sentiments. In the prompt itself, you give those examples. And then you say, okay, now tell me the sentiment of this sentence. So what is happening is it is learning based on the examples, it is able to learn how to classify sentiment. Okay, so that kind of in-context learning is something these larger models started exhibiting. And as you can imagine, that is very powerful. It sort of started people thinking in the line of, okay, is this some weak form of AGI, artificial general intelligence, that they're showing, so it has something magically emerged. So that is what is this emergent word. Instruction following. So again, they can also be fine-tuned to follow instructions. So it understands language, but then you tell it to answer questions. That is what ChatGPT, the web application, is fundamentally. So if you ask it questions, it's basically, or ask it to do something like summarize this essay, or do this or that task, it will do that. Okay, so instruction following, and then step by step reasoning. So it also started showing some kind of logical ability. So it could handle follow-up questions. So it gave you the first answer, but then you said, okay, now give me something more about this. Okay, and this is where the agents and all are being, they are showing the power. So the LLM itself is limited by its context. It can't handle, like, it doesn't have state by itself. So if your conversation becomes long, then it is not able to keep on conversing with you. But agents are basically, you are extending the LLM with some additional memory and tools, whereby it can use that memory and those tools to further enhance its knowledge. So one of the common things that was happening with LLMs initially is that their information was not up to date. So if the LLM's information cutoff was 2021, and you asked it about the post-pandemic world, what was going on, it couldn't answer. Okay, but now by enhancing it with tools where it can do web search or it can look up other information, it is actually able to sort of extend its abilities. So that is pretty much in brief what agents are. Okay. And the other thing that you will hear a lot is foundation model. So, India is talking about building their own foundation model. So there are a lot of LLMs, but a foundation model is where you are training it from scratch. So an Indian foundation model would be trained on regional language text also, so that it doesn't hallucinate. Today, if you ask ChatGPT to make up poems of some famous author of an Indian language, it'll usually fail. It'll generate something, but it'll be wrong. Okay, it'll be something out of hallucination, because the foundation model hasn't been trained on these things. So if you fine tune it for other tasks, so a foundation model can be fine tuned for specific tasks, like a foundation model which is trained on very large amounts of data, and it's very computationally intensive. But the fine-tuned models can be basically specialized for certain tasks. So on the right side, we show what the base LLM for GPT would do. So it predicts next word, that is its job. So if you give it, once upon a time there was a unicorn, then it will continue that lived in a magical forest with all of a unicorn friends. That is what it has been trained to do. The base LLM does only next word prediction. But then by giving examples of conversations and question answering, okay, there could be it was possible to form the instruction tuned LLM, which is what ChatGPT uses. So the difference is shown in the lower one. So if it was trained on data like which had what is lot of questions in what is the capital of France, after that the question would be what is France's largest city. This might have been there as the most probable thing in a question paper on which it was trained. But after it has been instruction tuned, if it is asked what is the capital of France, it will say the capital of France is Paris. So we know that it has to answer. So it has been fine tuned for that capability. So this again, there are a lot of things here, but the fact is that a foundation model is basically a general model which is mostly next word prediction, and then and that is huge. That is the more computationally intensive, difficult part. And because of the capabilities of LLMs, this ability is easily extended by fine tuning, relatively easily. Like you might need trillions of tokens or words. I'm saying token is another concept. So to train a foundation model, while you might need 1,000 examples to fine tune it for a particular task. And foundation LLM training, as I said, requires very heavy capability, and you have to have the right parallel algorithms and parallelization of the workload, and then the execution on hardware and software systems. So both parts are going to be there. So, and here you on the side you see E2E Cloud, which is India's top provider of cloud GPUs. So that is something which has become available in India because the government wants to use to build foundation models and that kind of thing. Okay. Now, another thing that I've put here is LLM compression. Now, you might have heard about DeepSeek, and you also, if you see the headlines on the right side, so it says DeepSeek copy of OpenAI. Okay, and then what is distillation? So distillation is basically using, if you have access, if you are able to use a larger model, you could ask it questions and pass data through it and see its output and then train yourself on that output. So it's sometimes called a student teacher model. That is one of the distillation models. So that is knowledge distillation. If you have access to a more powerful model, you may be able to train a weaker model by by asking questions to that more powerful model. And then there are other methods like quantization, where you basically use the hardware better. You represent the weights as smaller numbers. And pruning is again removing certain portions of the neural network. So these are the kinds of things that new companies are using, and sometimes they are using ChatGPT model with which they interact, and then they're able to sort of do these things. They're able to come up with smaller models which are less expensive to train. So this is something which has been going on of late. Okay, and now we go on to the Gen AI section. So
Hmm. Okay. Transformers and LLM is the section. So let's do the questions here. Why was the introduction of the transformer architecture revolutionary? So attention through, context understanding through attention mechanisms. Of course, it did not eliminate the need for training data that was definitely required. It enabled parallel processing of sequences. So this is another detail. Unlike the LSTMs, which were producing one token at a time, they were processing and training. This could take blocks as input, similar to how a convolutional network takes an image. And it simplified language modeling significantly. So that's also true. So that was the breakthrough. Which of the following statements about large language models are correct? LLMs can generate human-like text, we know that. They are trained on massive data sets, that's also true. They rely purely on rule-based systems, definitely not. LLMs have emergent abilities such as in-context learning. Okay, so now let's go back. Okay, so I will go to Gen AI. Now, the Gen AI is based mostly on LLMs. Okay, and sort of when you expand the LLM with tools and memory, then you get agents. So that this is the summary of this whole section. So Gen AI is a type of AI that focuses on creating new content. It's not in traditional ML, you are making predictions or decisions based on given data. So and they're able to make the predictions on unseen data. But here, the generative models are actually generating new content. Those could be usually text, but then images and all come in. But initially starts with text. So generative AI use case is you ask it to write an essay or you ask it to summarize text. That's also generative. It is generating new content. Okay, and it may completely rephrase the original text. So if it is doing that, it's proper generative content. But it is possible to summarize text by not being generative, but by extracting certain segments and trying to combine them. That's what older models were doing. That is not strictly generative, but generative is like you're creating new content, and it's mostly based on LLMs. When you come to generative AI, unimodal and multimodal are important concepts. So in unimodal, which is shown on the top, you give a text instruction. Please write a description of a horse. So this is the prompt that you give, and the generative AI model, which has been pre-trained on a lot of data, it's able to understand that instruction, natural language understanding, okay, and then natural language generation. So it does. A horse is a magnificent animal that belongs to the Equidae family. Now, the multimodal, if you see the instructions, the first instruction 2 in the lower picture, it says describe the horse, and describe this picture and gives the picture of a horse. So that the prompt is describe this picture and you give the picture of a horse. And then the model says this is a horse. Okay. And then the instruction 3, the prompt is provide a picture of a horse, which means generate a picture of a horse. So the model understands that and it produces the picture of the horse on the right. Or it could say write a song about a horse. So the instruction 4, that is the prompt, write a song about a horse. The generative model basically produces an audio file that includes a song about a horse. So these are the unimodal and multimodal examples. So for a long time, ChatGPT was unimodal. It was text only. But now, if you see, you are able to provide images to it and say, describe this image and do that kind of things. And actually, it's using agents also, because now you can ask it to search the web. You can ask it to run your programs. So those kind of things are happening. So it has gone from unimodal LLM to multimodal and agents with the stuff that we are discussing now. So commercial Gen AI platforms and models. So commercial side, we have the ones from OpenAI, Google, and Anthropic, and Microsoft. And on the open source, Llama 3, which is now actually you have a version present with WhatsApp now, and Mistral AI, DeepSeek. DeepSeek is also open source. Now here, it's important to understand that there can be different types of open source in this. So when the network weights are given to you or uploaded on maybe Hugging Face, then it is called an open source model. You can use the model, but there may be others. I think Llama 3 has done that. They also open source the data on which it was trained, and also the training code sometimes. So that is like full open source. But the commercial ones, you can't even, without using their service, you can't access. But for the open source, there may be different levels of open source. It may be that the weights are open sourced, and it may be the weights and data and training code are also open sourced. So usually today it's mostly the weights that are open source, so you can use that model. Okay. Now, if you are having to use GenAI to build your app, what kind of things would you do? So the first thing that came about, which was useful, is retrieval augmented generation. So this basically evolved into agents, which we will get in next. So in retrieval augmented generation, what happens is, because the LLM has limited context, you don't pass a whole document or all the data into the LLM and ask it questions. You don't. So if you have many documents, then basically you break it up into chunks and generate embeddings, as we were talking about. You generate powerful embeddings and store them in a vector database. And then when you have to answer a question, first thing you do is to look up the vector database and get some relevant chunks, so that you don't have that much data to send to the LLM, which has not only limited context handling capabilities, but also more cost. So collect all those chunks. You send just a few chunks saying that, okay, based on my vector search, I think the answer lies within these few chunks. And then you send that to the LLM along with the question. The LLM answers out of that thing, which is actually inline content for the LLM. The LLM is not using tools and all, but it is actually is stateless. So in every request, it has the whole context that is being sent by the client. So that is the first generation of LLMs. And how do you write these programs where you want to combine vector databases and other kinds of models and tools, as they are called? Uh, you would use a framework like LangChain, or you would code yourself. In your service, you have query this thing first, get this data, then ask the LLM for a response, pass that response to another model that I have myself to find something out from that. So this is how the first generation of applications or server-side applications were built. And a vector database is basically a database which can store embeddings, and if you give it text, it will generate an embedding. You have to tell how to generate. So, and then it will be able to do an embedding search using fast approximate neighbor matching. So in the vector space, it will do a fast lookup. So you will get a context sensitive search. To an extent, it is context sensitive. It's much better than the TF-IDF based search in many cases. Okay. Now the RAG example, as we were saying. So the question that is there is, what did the president say about Justice Breyer? And instead of passing this, now how will it answer? This question is present in a collection of documents. So you can pass all your documents to the LLM, but the LLM, because of its context, won't be able to answer from such a big content. And also it will be costly because it will have to process this whole thing. So instead, to break up your content, the black stuff, into chunks and create embeddings and store them in a vector database. Now, as processing of this query, you first query the vector database, get a few chunks, and then send this question, what did the president say about Justice Breyer, along with the chunks where you think the answer lies. And out of those chunks and the question, the LLM generates the response, which you then send back, which is the president thanked Justice Breyer for his service and acknowledged his dedication to serving the country. Now, this is generative response. This particular content was not there in any of the documents. The documents might have had different kinds of information, but after it was looked up in the vector database and the chunks were sent, like the chunks are showing, today I'd like to do this and I hear that. So there was some kind of um, logical reasoning and answer generation that the LLM did out of the limited things that were passed to it, the limited chunks. So that is RAG. And then, as I was saying, you come into LLMs. So LLMs have is like advanced AI assistant. It's capable of reasoning, decision making. So at its heart is an LLM. Okay, it's able to do, it's able to do reflection, critique itself, chain of thought. So it's getting more and more human, basically planning. So this has been the vision of AI for a long time. The very old AI books, these kind of things are talked about, but now it's becoming reality. And after this reasoning, the agent is going to use its tools to carry out actions. Even as part of the reasoning, it might have to gather data through tools, and then it might carry out actions through tools as well. Okay, so that is the idea of an agent. Now, and at the heart of the reasoning engine is the LLM basically, and it's using tools for other things. So let's look at what an agent means. Uh, so when you were using ChatGPT at the beginning, if you could ask it, plan a trip to New York with this information. I want to start at this time and come back on this date, and I want some stopovers here, and then it will generate something. But here, the agent, you start talking with an agent, just like you would talk with a travel agent. So it tells you that I can do all these things now, and I'll also add it to your calendar after it is booked. So you tell me what you want, and you give it some higher level requirements, not like exact departure dates and all. You say that I want to go at this time and at this week, particular week, and I want to come back after 2 weeks. And you have some freedom on how to plan it. So please go ahead and suggest what kind of plan you come up with, and I will say if it is okay, and then you can actually do the booking and set my calendar and all these things. So that is the more advanced version, where the agent has to do a lot more reasoning, and it has to have access to tools. It has to actually be able to look up tickets with travel sites, and make bookings, and then it has to be able to look up hotels. It has to also find current events by doing web searches. It has to find out about the weather. So it has to do a lot of things. The reasoning engine is the LLM, but it's using other tools. And then after some time, okay, a more advanced agent will, maybe the agent will pop up and say, I think you are having a tough time. Do you want to travel somewhere? I can plan a whole trip. I will choose everything. I know what you like. Okay, I already know all that, and then I will suggest to you that this is where you should go, and it might help you. So that is a more advanced agent, okay, which is not there yet, but we could reach there. So the vision of agents, basically, again, whatever we were talking about. So it's basically, there is a reasoning engine which is acting almost like a human, and it's able to do a lot. Basically, it's able to do lots of different things. It's able to interact with external systems, get information, reason about that information, take actions. So this is basically the talk right now, the latest in AI, agentic AI. Okay, so now I think we are almost close to the end, and now we go to, sorry, I'll have to share, I think. Okay, so we go to generative AI and agents. Okay, so which of the following technologies are commonly used in generative AI? So not convolutional neural networks, they're used for computer vision. So generative adversarial networks are used, but not in the LLM form. Okay, so these are pre-LLM, as the name says, generative. Okay, reinforcement learning, yes. Okay, you have to, they use powerful models, will have to use that to learn on their own, not being retrained every time. So based on feedback, they will be able to collect their own feedback and do transformer based models, yes, of course. What are the common applications of generative AI? Creating images and artwork, yes. Generating synthetic data for training models. This is very important. So we have done a lot of this. So it does a very good job of doing this for training other models. Okay, so you generate data for training other models, lighter models. Predicting financial markets with 100% accuracy. That is not something anybody can do. Okay, so developing AI chatbots, yes. Okay, AI agents. What distinguishes AI agents from traditional AI models? So agents can autonomously plan and take action. So there's a planning and reasoning is their uniqueness. AI agents work only with structured data. No. They can integrate with tools for decision making. Yes. AI agents never require human intervention. No, that's not true. Usually, even with a person, if there's a travel agent, for example, they'll ask you, right? I mean, you say whether the plan is good for you. That they can't do on your behalf. So some level of human intervention has to be there. So which AI architectures support AI agents or transformer? Yes, reinforcement learning frameworks, LLM based reasoning, not simple LLM based logic. Okay, so now we continue to the conclusion. Okay, so in conclusion, we come back to the slide we already saw. We revisit that. Okay, just so that can recap it a bit. So we are at the artificial narrow intelligence state, almost at the high end of capabilities of that with agents. So here from 2012 onwards, you can say that from ML we went into AI, where human-like tasks were there with object detection, summarization, translation. But when it went into chat GPT and AI agents, based on what we have discussed, that is like it's sort of intelligence. Okay, it is not quite human-like, but it's almost approaching like that kind of level. So still narrow intelligence or weak AI, and then general intelligence is even more. So whatever humans are able to do, it will be able to do all that by itself, autonomously. And for that, one of the things that is felt is that machines have to understand what they're doing. So even today, nobody believes that machines understand what they do. I mean, they are able to sort of fake humans, but are they actually understanding what they're doing? Yes, they are doing a lot of things very similar, but are they at human level yet, or will that ever happen, or is that something that cannot fundamentally happen? Those things are not known. And if it can reach artificial general intelligence, then based on the power of machines, the super intelligence is probably, I mean, going to happen. And that has been the theme of science fiction movies for a long time, whether it is 2001 A Space Odyssey from the late 60s to, maybe this one, Terminator or Matrix. So, and then the use case. So here we talked till generative AI. So autonomous agents is the next step. And what could they do? Determine good campaign timing, design campaign, run campaign, monitor, evaluate, optimize for next campaign. So it could do all these kind of things. Okay. So that brings us to the end, but there are a few small questions that I think in the remaining time we'll quickly cover, so that there are things about AI ethics and implications. So we didn't talk much about that. So we could just briefly cover it through these questions here. Okay, what are the key challenges in AI development? So bias in training data. Okay, if your training data is, this is a big topic always, that if you are using it on training data that has political or social bias, for example, then you would give certain that kind of output. Of course, there are techniques of reinforcement learning that are used by the models. One is called RHLF, reinforcement learning with human feedback. So humans are asked to evaluate the LLM responses, and reinforcement learning input is provided back to the model so that it knows what kind of data output it is better suited. High computational costs, of course, mostly because of the GPUs and the high-end hardware that is required. AI systems always achieving perfect accuracy, that is not required. Even humans are not 100% accurate. You need 100% accuracy for particular calculations only. Other things are like anything which involves humans or any kind of human qualities, there will be some error. That has to be minimized, and that has to be also explainable, which is the next one. Interpretability of AI decisions. This is something it might be doing the correct thing or the wrong thing, but it's hard to get it to say why it did that. Now that is also improving. That's an area of that's going on. But if you think of it, um, that's a higher level skill as well. Like now, programs are written by humans after putting in all the explainability. Right? I mean, the explainability is what you are coding. You are coding because you are defining that that is how it works. But when you get into more subjective things, then the perception gives the answer. Then you might have to ask even a human that, okay, you said it is a dog. Well, why do you think it is a dog? So then that involves some more processing and some more contemplation and thinking. So it's not instinctive. So it's natural that it's not a fault of the AI, but the whole nature of interpretability and explainability is like that. Okay, what differentiates weak AI from strong AI? So weak AI is designed for specific tasks, and then strong AI exhibits general intelligence. So strong AI is basically AGI and ASI. Okay, so AGI is strong in the starting of strong intelligence, like humans. Weak AI can surpass human intelligence. No. Strong AI can reason across multiple domains like a human. Yes. Okay, so it will be able to find out information and learn things that it doesn't know about. So, which fields have been transformed by AI applications? So, yeah. And these answers are all self-apparent. They're more for learning rather than any test. It is more for reinforcing what we discussed. Okay, if a deep learning model is overfitting, what can you do to improve its performance? Now, we didn't talk about this, but I'll just mark the answers so that those who know about this can. So you don't want to increase the training epochs because it is already overfit. So use dropout regularization. This is a technique where you sort of make it a bit, you sort of remove some of the you know the knowledge which has made it overfit. It's like particular for that very you make it more general by removing some of its knowledge. In effect, increase training data, yes, because it is overfitting. It means more data. Reduce the number of parameters, yes, because this model is too heavy for the use case. An AI system incorrectly classifying customer reviews as negative. What steps can you take? Yeah, so you have to check your data. So is it all negative sentiment that was trained on negative reviews? Adjust model hyperparameters. Okay. Ignore the issue as AI is never perfect. Yeah, this should never be done. Okay. Fine tune the model with better label data. That is obvious. Okay. Why is explainability important in AI decision making? Helps build user trust. Now, reduces computational costs? No, I mean, explainability will require more processing, more cost. It ensures ethical AI use. It's able to say why it did something. Say, for example, you have an AI system for evaluating an answer to a question, a subjective answer, and it marks it wrong. And just like with your teacher, you may have that discussion that why is it wrong or why is it, what is inaccurate about it. So it should be able to explain. It allows humans to understand AI generated outcomes. Yes. Okay, which of the following trends will likely shape the future of AI? Increased use of AI agents, development of AI ethics regulations, yes. Slower adoption of AI across industries. Yeah, not everybody will be ready to adopt because there will be challenges that we talked about. Integration of AI with quantum computing. So this will happen. Now, this actually, is debatable. I mean, it's because it is so fundamental, some adoption will happen. And integration of AI with quantum computing. So there is some talk going on, but again, quantum computers is another area where a lot of progress is claimed from time to time, but we don't know. Somebody says 20 years, somebody says never happened, somebody says 5 years. So we'll have to see. So what are the potential risks associated with advanced AI? So bias and discrimination, AI replacing human jobs overnight. So this is like very far-fetched. Some jobs may be replaced, lower skill jobs or things which are better done by AI, but that will free up humans for doing the next level of work. So as long as people are more flexible about learning and using these tools, mostly the view is that it can actually generate jobs. Yeah, some jobs will go for sure, but there will be others generated. So that's why it's a good idea to invest in understanding and using this whole field. Misinformation generation, yes, a lot of it already happens. There's a lot of junk content going on the internet. Uh, Security vulnerabilities in AI systems, yes. So for any use, this is extremely important. So there are attacks already, like prompt injection attacks, similar to SQL injection, which I've talked about. So yes, this is security is always going to be important in any important system, not just AI. And for AI, because unless it is explainable and all, these things will continue to remain as serious challenges. Okay, so with that done, and I think we are out of time as well. So let me see, there is something on the chat. If machine learning data is crowdsourced, does every new LLM launched in the market for the has to crowdsource data from its scratch, or do they acquire data from existing LLMs built by other companies? So they can't get the data directly, but they can get it by answering questions. So for example, DeepSeek could create its prompts and ask a lot of things to a lot of questions to ChatGPT and get those responses and treat that as its sort of a training set or a fine-tuning data set. Okay, and that is how the process of distillation usually works in the case of LLMs. Okay, so okay, thank you. Okay, thanks everyone. I think we are out of time as well. Just managed to finish on time. Okay, okay, good luck. Talk to you later. Thank you.